Here's the 1988 E&M free response test, problem number 2. And so let's go over it. It says, in the circuit shown above, the battery has been connected for a long time so that the currents have steady values. Given these conditions, calculate each of the following. We want to know the current in the 9 ohm resistor. And, well, actually, we'll just go through it one at a time. So we want to know the current in the 9 ohm resistor. Now, when they say the current has been on for a long time, what's the significance of a long time? Okay, everything's maxed out. Now, basically, there are 2 circuit elements that we have that are transient or that vary with time. Not resistors, but we have capacitors, which can fill up with charge, or inductors, right, which can reach a maximum current, and then there's no voltage drop across them anymore when they've reached their maximum current. So we don't have an inductor here, but we do have this capacitor. Now, if this has been on for a long time, what does that mean is true about this capacitor? It fills up with charge, and thus there's no current flowing through it. Now, what's the significance of that? Well, now that this thing, there's no current flowing through it, if you're the battery that pushes current through here and it comes down, it goes through this 8 ohm resistor, all that current goes through the 4 ohm resistor. All the current that goes through the 8 ohm also goes through the 4 ohm resistors here. Yes? Why doesn't it go through the capacitor? Because the capacitor is full of charge. Now, if you look at it right when you turn the switch and turn the circuit on, a little bit of the current, or maybe actually most of the current, went through it like this at first to fill it up. But once it's filled up, it's not going to have any more current flowing through it. A full capacitor, there's no current. That might be one of the big ideas you write down. Full capacitors means no current through that capacitor. Obviously, right? I mean, if there was a current into the capacitor, you're putting more charge into it, right? That's what current is a flow of charge. So that means that this 8 ohm resistor and this 4 ohm resistor are in series. It's almost like you could just ignore that capacitor. Okay? So now, to figure out the current through this 9 ohm resistor, what I need to know is what is the total current? Because that's the total current, is all the current runs through the 9 ohm resistor. So all we need to do is figure out what the equivalent resistance is. Okay, so so what I like to do on the AP test to save time, I like to circle things. So what is this 8 ohm and 4 ohm resistor?
12.
It's 12. So we have so R equals 8 ohms plus 4 ohms equals 12 ohms. So why am I writing it down? To get credit, to get points. So at least write it down. All right. So now, so this has got 12. Now think about it. Everything up here is at 1 voltage. Everything down here is at the same voltage. So this 4 ohm and this 12 ohm equivalent resistor are in parallel. So I can figure out what is this? What is this whole thing? Well, the resistance of that is going to be 1 over 1/4 plus 1/12. Okay, so these are resistors in parallel. And you got to write it down. Don't do it in your head. I mean, this problem is easy enough to do it in your head. Don't do it in your head. Write it down so you can get credit for it. So what is 1/4 plus 1/12? Okay, that's 4/12. Reciprocate and divide, you get 3. So this is a 3 ohm resistor. And now I've got a 9 ohm resistor in series with a 3 ohm resistor. So the total R equivalent, you can close the door over there. That R equivalent is the 9 ohms plus the 3 ohms. This is 12 ohms. So actually, I'm doing part A right up here on the test itself. Okay, so now I know what the total resistance of this whole thing here is 12 ohms. Now I can figure out what the current is through the 9 ohm resistor. Right, delta V equals IR. And so the total current is equal to the total voltage, which is 120 volts, divided by the total resistance, which is 12 ohms, and that's going to be 10 amps. So there's my answer for part A. Yes?
Okay, so the current through the 9 ohm resistor is the same as the equivalent resistance because you combine those bottom 3 resistors into kind of like one.
Right.
Right? So then that means the 9 ohm and then the 3 combined ones would be in series then, right?
Right.
So that's why you can combine the,
right.
the 3 and you get 12 in the end.
Yes.
Okay. I was thinking,
okay.
Like, why would you
so Emmanuel's not here. Okay.
Why would you have the equivalent resistance? Because that might drop.
Well, you need the equivalent resistance of all of this because you want to know what the total current is. Because the total current is what's flowing through the 9 ohm resistor.
Right.
Okay?
That makes sense.
Yeah. All right, so now we want to know now the current in the 8 ohm resistor. Okay, now to do part B, I'm gonna go down. I'm gonna do it down here. And the current in the 8 ohm resistor, well, now I redraw the circuit because this is getting so messy. So here's 120 volts. We got 9 ohms, and then we have 4 ohms. And then over here we have the 8 and the 4. And notice I'm not even worrying about that capacitor. I'll do the capacitor later when they ask about it. So they want to know what's the current through here. Well, notice that the current through here is just the current through this branch right here. So the current through the 8 ohm is the same as the current through this 4 ohm. But what was this? This was a 12 ohm. Now I can figure out what the current is if I knew what the voltage drop is. I know what the resistance is here. It's 12 ohms. If I knew what the voltage drop was here, I could figure out what the current is. Well, I know what the total current is. It's 10 amps. That means that I can figure out what the voltage drop is here. So on your drawing of the circuit, you show your little calculations. Delta V across here is 10 amps times 9 ohms, which is 90 volts. So I've got a 90 volt drop from here to here. I've got a 90 volt drop. Well, if I go all the way around the circuit, how much, I need 120 volts of drop. So if from here to here is 90, and then from here to here has to be the rest. So what's the total voltage drop from, if this is 90, so you go 120 volts minus 90 volts. So what is this? This is a 30 volt drop from here to here. That means that the current in here, I can figure it out. I know delta V equals IR. I solve for I equals delta V is 30 volts divided by R. Now I know they want the current through the 8 ohm resistor, but I'm just trying to figure out the current in this branch. So I need the total resistance of this branch, which is 12 volts. I'm sorry, 12 ohms. And what is 30 divided by 12? It turns out to be 2.50 amps. And that's my answer for part B. Now these circuit problems are kind of messy because it's all a little bit of delta V equals I, or a lot of Ohm's law things. So draw it and kind of show what you're doing, and you'll get the credit that they want, that you want to get. Any questions on part B?
Can you just explain the last part again? The last last part of that, where like
Right here?
Like, and you just use the combined resistance of 8.
Well, sure, because look, it's going to drop from 9. What is it at here? It's at positive 30, right? Well, it's 0 here. Goes up to 120 voltage band, up to 120. Now it drops 90, so now we're at 30 volts.
Right.
Then we got to drop back down to 0. So I got it from here to here. I got to drop down 0. But to go from here to here, I got to go. I got 12 ohms of resistance. So that'll tell me how much current will be allowed to flow through that branch.
So, what if? Hold on.
Okay, well, I got to move.
Okay.
I got to move on. Save your questions. All right. Now for part C. The potential difference across the 30 microfarad capacitor. Okay, so now we're back in the capacitor. So what I could do is redraw it in here. So there's my capacitor again. And then I just write delta V for the capacitor is equal to the delta V for the 4 ohm resistor. You know, and I can even draw like up here. Now remember, you're trying to show the grader what you know, and you're trying to do it quickly. So try to be clear, as clear as you can be. It is difficult though. Well, look, I now know what current is flowing through here. That's equal to I, R. Well, what is the I through here? We just calculated it to be 2.50 amps. And this is 4 ohms. And 4 times 2.5 is 10. 10 volts. So since this drop here is 10 volts, that means the drop across the capacitor is 10 volts. And that's my answer for part C. Make sense? Okay. And let's do part D. So, I mean, actually, the big idea here is circuit elements in parallel have the same voltage drop. So, there you go. Now, it wants to know the energy stored in the 30 microfarad capacitor. You look on your equation list, the energy stored in a capacitor. Well, I don't know the charge, but I know the capacitance. Now I know the voltage drop. One of them is 1/2 C delta V squared. Remember that one? If you don't remember that, that's a good one to memorize. There's 3 of them, right, for the energy stored in a capacitor in terms of the capacitance and the voltage, the capacitance and the charge, and the charge and the voltage. There's 3 combinations there. But anyway, this is 1/2 times 30 microfarads, and delta V is 10 volts. Got to square that. So this is what? Well, this is 100 divided by 2 is 50. 50 times 30, that's 15 with 2 zeros on it. And we have a micro here. Microjoules, so 1,500 microjoules. I mean, if you want to put it in terms of joules, you can. Okay. So let's zoom out as much as I can. And so here's the whole ABCD. Now, if you got through all this, in my mind, A, B, C, and D are very doable. You can at least get lots of partial credit for it. Part E turns out to be, at least for me, it was very hard to do. So I'm going to try and do it right now. I prepared by doing it the other day. But it's kind of crazy. At some instant, oh, and by the way, if you look at the solution guide, this is worth about 4 points or something. If you've done A, B, C, and D, you've got a lot of points. And you can, if you get to something where you're stuck, move on and get the easy points from the next free response then come back to it if you have time. But don't spend 20 minutes trying to get 3 or 4 points. All right. So E, I'm gonna do on a separate paper here. Let me zoom in though. It says calculate the total amount of energy dissipated in the 8 ohm resistor after the connection fails. So here's our connection P right here. Oops. Right here. And it fails. Now what does that mean? Current can't flow through here anymore. The battery is out of the circuit. The 9 ohm resistor is out of the circuit. Boom, there's my circuit right here. This thing. So I want to know, now that means that this capacitor that's full is now going to discharge. So we have a discharging capacitor. And we want to know how much of the total energy dissipated by the capacitor is dissipated through the 8 ohm resistor right here after the connection fails. So in other words, out of this 1500 joules or 1500 microjoules, how much of that 1500 microjoules is going to go out this 8 ohm? Well, there's resistor. There's an easy way, but it's very intuitive and it's not very satisfying. Then there's the hard way, and I'll try to do it both ways. Now I'm just explaining this to be complete. Actually, for most people at this point, I would expect you to move on to the next problem if you have 45 minutes. But if you see how to do it, go for it. So here's E. Now I'm going to redraw the circuit. Here's the thing, if these two guys are gone, this 8 ohm and this 4 ohm resistor are in series with each other, right? Because all the current that comes through this branch has to go through both the 8 and the 4 ohm resistor. So these two guys are now in series. Okay, so I'm going to draw, here's the 8 ohm and the 4 ohm. They're now in series. Now look at this. From here across to here, it's going to be the same voltage drop. Well, from here, I'm not on screen, I'm sorry. From here to here is the same voltage drop as from here to here. Therefore, this and this are in parallel. So the 8 and the 4 ohm resistors are in parallel with the 4 ohm resistors. So I can draw it like this. And of course, the 4 ohm and the 4 ohm resistor and the 30 microfarad capacitor are in parallel as well. Now, here's something that makes part E actually really easy, or quick anyway, not necessarily easy. If you recognize that, okay, this has this 30 microfarad capacitor. Well, the energy stored in here is 1,500 microjoules. But this is going to push current out. Now, the energy dissipated through this resistor is going to be a fraction of this energy. Now, this has 12 ohms of resistance total. And this is 4. So how much current is going to go through here as compared to here? Well, 4 ohm, 4 ohm, 4 ohm, 4 ohm. It's almost like there's 4 ohm, 4 ohm, 4 ohm. And so basically, this is a 3-to-1 ratio. The resistance here compared to the resistance here. So that means that only 1/4 of the current is going to flow through here. 1/4 of the total current is going to flow through here as flow through here. So you have 1/4 of the current flowing through this 8 ohm resistor. Now, for that, what fraction of the energy that's dissipated by the current, by the energy that's carried by the current through here is going to go out the 8 ohm. Well, 8, there's a 2 to 1 ratio here, 2 to 1. So 2 plus 1 is 3. So 2/3 of the energy dissipated by this branch is going to be dissipated through the 8 ohm resistor. So basically, if you go 1/4 times 2/3 of 1,500 microfarads, you'll get it. So let's see, what is that? That's 2. So what's 1,500 divided by 6? It's 1, 2, I think it's 250. Is that right? Microjoules. And that's the answer. All right. No, that's the easy way to do it. Oh, I mean, relatively easy in terms of computation. And you had to see this in terms of fractions of currents and all that. Now, there's another way of doing it. I looked in the solution guide, and I went, wow, this would take too long. The other one is this. Well, I don't know if I even want to. Well, we might as well. Yeah, we might as well do it. This is really a dissipating RC circuit. So what's the equivalent resistance of this whole thing? Yeah. Yeah, 1/12 plus 1/4. We already did that, right? It's actually 3 ohms. Right? This is the equivalent of all this is 3 ohms. And we know the capacitance. So we can figure out what the time constant is for dissipating all this. I mean, if I was going to look at the charge on this capacitor as a function of time, it would be, actually I should use lowercase q. It would look like this, an exponential function. Now, by the way, the reason I'm going over this like this, even though you didn't really need to do that for this test, there are other tests to come where you have to draw these exponential functions. And here's RC right here, the time constant, RC. So RC is equal to the resistance, which is 3 ohms, times 30 microfarads. So that's going to be 90 microseconds. That's the time constant here. Now, since the voltage okay. So I'm going to be using that here in a minute. Now, going back to the energy dissipated by here, I'm going to show you a very sophisticated but very rigorous way of doing it. This is going to have a certain current flowing through it. And the power out that 8 ohm resistor is going to be equal to I squared R, where R in this case is 8 ohms. But the energy that goes out is equal to the integral of power times time. Power times time is equal to the energy. You can use E if you want energy dissipated, or this is potential energy. So I'm just going to use, I don't know, E. E here is not electric field. It's the energy that goes out of it. And we're going to go from 0 to infinity. But I need to figure out what the current is. The current is a function of time. I know what R is, and I'm going to take this and I'm going to substitute it in there when I do the integration. But let's figure out what I is. I depends on the voltage drop. And so the voltage, I'm going to say this. The voltage, well, what's the maximum voltage? Where do we start? We started with 10 volts. And then we're going to dissipate. The voltage on the capacitor is going to go to 0. It's going to have this exponential. So now we know what the maximum value is. It's just going to be e to the negative t over RC. So this is the voltage that's available that's provided by the capacitor.
So that's the voltage is a function of
Right.
sort of the whole circuit.
This is the voltage that's supplied by the capacitor that's driving the currents through those resistors.
Okay.
Now I need to figure out what the current is through the 8 ohm resistor, which is the same through this whole branch, which has a 12 ohm equivalent. So we know that V equals IR. So I equals V over R. So that's going to be 10 volts times e to the negative t over RC. And we know what RC is. But to figure out this current, what resistance should I use? Do I use the 8 ohms? No. Do I use the 3 ohms equivalent for the whole No. Because this current is going through these 2 resistors. So it's 8 plus 4. It's 12 ohms. Yikes. So here's what I've got for current. The current is equal to 10 divided by 12, or 10 volts e to the negative t over RC over 12 ohms. That's my current as a function of time. So now I want to find power. So power is equal to this squared. So it's going to be, now by the way, let's go ahead and simplify it. Where's the calculator? What is 10 volt? Well, it's going to be 10 volts over 12 ohms. And we're going to square that because it's I squared times e to the negative t over RC, but I'm squaring the current. So what happens when you square this exponential function? You get a 2 right there, right? Correct? You follow that? Pay attention. You know, look up here. So this gets squared. All right? You with me, sort of? I know this is long. Times R. Well, what is this R? This is the power out the 8 ohm resistor. So you want this to be 8 ohms. So the power as a function of time is equal to, well, let's get rid of the constants and concentrate them all in one. So this is going to be 10, and then you got to square it, and then, so when I go 10 divided by 12, square it, multiply it by the 8, I get 5.556. And by the way, what are the units for this going to be? Volts divided by ohms, that's amps, amps squared times ohms. What is that? What units is that going to be? Or you can just look at it. What does it have to be? Has to be in watts. Right? Because this is power. We're calculating power. I squared R turns out to be watts. So this is 5.556 watts, okay, times this exponential function. Now, what is, by the way, what are the units associated with the exponential here? Doesn't have any units, right? It's an exponential function. Now, you're multiplying it by this constant that has units. So that's why it's power. Now we're ready to figure out the energy dissipated by that resistor. Because I have this. So I'm going to take this, and I've run out of room on this paper, so I'm just going to put it over here. So the energy dissipated by that from 0 to infinity is the power function 5.556 watts times e to the negative 2t over RC times dt. All right? Now, this looks horrible, but you know how to do this integral. Well, okay, yeah, I'm old school. Now this is 1 over 2 over RC, negative, right? It's that I think the integral of e to the ax is equal to 1 over a times e to the ax. From your, I think, and on your equation list you have that integral table. Okay. Times e to the negative 2t over RC. This stays the same, evaluated from 0 to infinity. So now let's do this. E is equal to negative, here we have the negative, 5.556 watts. I think you can see now why I would skip this problem if this was on the AP test. Times RC. What is RC? It's 90 microseconds divided by 2. Okay, and then we're going to evaluate this. Well, when I put infinity in here, I get 0. And when I put 0 in there, see 0 minus, I get 1. So all this does now, we go from 0 to infinity, because like from time equals 0 to time equals a long time, right? That's all the energy dissipated by that resistor. So the negative goes away. So E is equal to, the energy dissipated is equal to this 5.556. Let's see, let's divide it by 2. Let's multiply by 90. And hopefully, woohoo, I get it. 250 microjoules, which is the correct answer. Now, the sad thing is, if you had just seen, oh, it's 1/4 times 2/3 of 59, you get 250 joules, you get the same amount of points as if you go through all this work. Now, hey, you guys, it was worth it, though. To me, it's worth it to go through both solutions because there are problems coming up where you need to be able to solve these, use these exponential functions and RC circuits and stuff like that. And by the way, exponential functions, they're really important to understand in biology, in economics, as well as physics applications. They come up all the time, and they're really kind of neat. So anyway, that is all for problem number 2. Only took me 35 minutes. Not bad, not bad.